In the earlier session we had seen the data structure AVL trees. We had seen that binary search trees in the worst case may not be very efficient, and so saw a height balancing property which made it efficient for searching, which were precisely the AVL trees. We also looked at insertion in AVL tree, and we also proved that if AVL tree is going to store n items, then the height of this AVL tree is going to be of order log n. This session we look at how to do deletion operation on the AVL tree. Like insertion in an AVL tree, where the first step was to insert as though we were inserting into an AVL tree. So, the first step also is going to be similar in an deletion procedure. So, we would delete as we would have deleted in a binary search tree. That would mean we are going to delete always an node at the last level. So, deletion, as you recollect, in a binary search tree always happen at the last level. If you recollect, the three cases that we had considered, one is the key to the node to be deleted has no children, or has one children, or has two children. When I say children, these are non-external nodes. External nodes, as we know, are always going to be null nodes or placeholders. So, depending upon one of the three cases, we are going to perform our deletion operation. So, this particular example, we want to remove key 32 from the AVL tree. So, 32, as we see, is a case in which it is a node which does not have any children. When I say again children, these are non-null children. So, 32 is here, and we want to delete 32. So, deleting 32 would mean we simply going to drop it from our AVL tree. So, the resulting tree is shown here. Let us try to check whether the tree now that we have got is an AVL tree or not. That the binary search tree property is still satisfied comes from the fact that deletion is as in a binary search tree. So, to check the properties, again we are going to look at the node which has been removed and look at a path up to the root and try to check the properties. So, if you look at this now, so this particular node is going to have height 1. So, whereas this particular subtree is going to have 1, 2, 3. So, 2 and 3. So, height of this is 3. So, if I look at this 44, then your height property, height balance property is violated at this particular node, because its left subtree has height 1 and its right subtree had height 3. So, the property is violated at this point. So, this imbalance has to be rectified. We had also seen how to rectify this property. Recollect, there were 4 cases depending upon how we are going to map x, y, z onto ABCs. So, we are going to have a similar convention also for removal. So, we will call Z as the first unbalanced node encountered while travelling up from the tree from W. W is a node which has been deleted. So, we travel from that up to the root, up to the, and mark the first node where there is a height property violated as Z. We are going to mark y as a child of Z with the larger height, and x is going to be child of y, defined as follows. If one of the children of y is taller than the other, choose x as the taller child of y. Y is always uniquely determined because we know at Z there is a imbalance. So, at imbalance, definitely one of the trees, either left or right, is going to have a larger height than the other. For x, it can happen that both children of y have the same height. Then we will select x to be the child of y on the same side as of y. To break the deadlock, we are going to use the convention that x is going to be on the same side as of y. If y happens to be a left child of z, then x will be left side of y, and if y is the right child of z, then x is going to be the right child of y. So, with this convention, which was similar to what we had for insertion, we have the following case. So, we are going to have z here. So, z is going to be the node where the imbalance has occurred. Y is going to be root of the right subtree, because that is the one which has larger height than the left subtree of z. So, y is going to be here, and x is going to be either the child with a higher height, or in case of a tie, in this case we can see that there is a tie, both the subtrees of y have height 2. What we see is that at y, both the left subtree as well as the right subtree has height 2. So, we break the deadlock by choosing x as on the same side of y. That means, since y is a right child of z, x we will choose as the right child of y. So, x is marked here. So, once we have marked x, y, z, like in insertion, we relabel them as A, B, C, as they would have occurred in the in-order traversal. Right? A should come before B and B should come before C. Once we do that, we do this mapping. Right. So, this mapping is done so that if you do a pre-order traversal, if you do a in-order traversal of the tree, A should precede B and B should precede C. And these are, you can rename this as T0, T1, this is going to be T2 and this is going to be T3. So, X, Y, Z, T0, T1, T2, T3 are going to be the structures that are going to be involved in our trinode restructuring. So, if you recollect, this is a case of a single rotation of trinode restructuring. So, the node which is called B will go and replace the node which is originally Z. So, we will have a single rotation. So, this is going to be a single rotation case of trinode restructuring, and T0, T1, T2, T3 will be restructured so that the in-order traversal of the new tree remains same as the in-order traversal of the unedited or of the earlier tree. So, if you look at this, so this is your T0, this is T1, this is T2 and this is T3. So, that if you look at the in-order traversal now, they would be precisely same. In this case, you will have T0, then you will have 44, then you will have T1, then there will be 62, then you will have T2 which is empty, 78 and T3 which is exactly the same as what you have in the rearranged or restructured tree. Once you do this, unlike insertion, this restructuring may upset the balance of another node which is higher in the tree. So, we must continue checking for balance until the root of the T is reached. So, we will check once more. So, once we have restructured at this particular stage, we will again go higher and check at the root whether the property is satisfied or not. So, now we can see that if you look at this as your root, its left subtree has height 1, 2 and 3, whereas its right subtree has height 2. So, it is balanced. So, in this particular case, we see that the local restructuring achieves the complete balance of the tree. We will also look at an example where this particular thing fails. That means, local restructuring may not yield a AVL tree or may not actually yield a AVL tree. We look at one more example, in which case local restructuring does not yield a AVL tree. That means, the height imbalance is propagated one level up. So, let us look at this case where in which an AVL tree we are going to delete the node which is going to store the value the key 4. In this, again in this example, we are not shown the external null nodes. Now, this is a case where the node has no children which are internal nodes. So, we simply delete it from the AVL tree. Now, we try to look at the height at on the path from the node which is deleted, which we are going to call as W, to the root. So, we check at 3. Now, at 3 it is left. So, we are going to have an null right child of 3. So, this height is going to be 0, whereas height of this is going to be 2. Okay. So, remember there are null nodes at the last level. So, there is an imbalance at 3. So, we identify x, y, z now. So, this is going to be our z, this is going to be y, and this is going to be x. Also, we are going to relabel them as A, B, C, as they would have appear in the in order traversal of the tree. So, in the in order traversal, this would have come first, this would have come second, and this would have come third. So, after doing a single rotation, we are going to rotate, we are going to replace Z by a node which is labeled B. So, after rotation, we are going to get this precisely as a tree. So, 2 has gone in place of 3 and the structure has been rearranged. Now, we see that height imbalance is propagated one level up. So, let us look at the root which is storing the key 5. Its left subtree will have height 2 and the right subtree is going to have height 1, 2, 3, 4. So, the difference between heights of the left and the right subtree is more than 1. So, we have imbalance at 5. So, we see that restructuring in the first case, that is restructuring at node 2, did not yield a AVL tree, but the height imbalance was propagated one level up. In this particular case, your one level up happens to be the root of the tree. Now, we try to identify x, y and z. So, this is going to be your z. Z is the node where height imbalance is present or the height property is violated. Your y is going to be a child of z which has a higher height, which is going to be y. So, this is going to be your y, and x is going to be the higher child of y with higher height, which is going to be here x. So, once you have identified z, y, x, we are going to try to relabel them using A, B, C, such that A would have preceded B and B would have preceded C in the in order traversal of the tree. So, this would mean this is A, this is going to be B and this is going to be C. Now, this is precisely again a case of a single rotation in the restructuring, in the trinode restructuring. So, we are going to replace a label node with label Z by node with label B. So, we are going to do this restructuring. So, this actually becomes the root of the tree now, and we do the restructuring so that in order traversal does not change after the restructuring. Once we do this restructuring, we see that we are at the root of the tree, and so you have no node further in the tree to check for height property. So, the restructured tree is going to be an AVL tree. So, this is an example where height imbalance property is propagated a level up after the local restructuring. Let us look at the running times of this, all the procedures. If you look at a single restructure operation, they depend only upon pointer adjustments and is based upon the linked list structure of a binary tree. And these operations are either one of the 4 cases that we have seen, whether it is insertion or deletion. We have seen that there are only 4 possible cases in which property can be violated and you need to do a trinode restructuring. So, what we observe that it does not depend upon the size of the AVL tree, it just depends upon the local structure of the 3 trees, of the 3 nodes that are going to be involved in the restructuring. So, it takes a constant time, as it is independent of the size of the tree. We say that a single restructure operation will take you a constant time. Now, let us look at the query procedure. So, the query procedure or search procedure is exactly going to be like a binary search tree, and we know in a binary search tree the search or the query operation is proportional to the height of the tree. In the case of an AVL tree, we know that if the AVL tree is going to store n items, then its height is of order log n. Therefore, the search operation or a query operation in an AVL tree is going to be of order log n. We also know that for querying there are no restructures needed, we are not editing the data structure. Now, if you look at the insert operation, we know the insert operation requires first to insert as we are inserting in a binary search tree. We know that this procedure is going to take time proportional to height of the tree, which in this case is log n. So, the insert procedure as in binary search tree would require order log n time in a AVL tree. Once you insert, we know we have to check for height imbalance, and if there is a height imbalance, one has to do trinode restructuring. we also seen that a single tri-node structuring is enough to make this into an AVL tree. So, insertion as in binary search tree takes log n time. If AVL tree property is violated, restructuring it so that new tree is an AVL tree takes a constant time. Therefore, the total time to insert is proportional again to log n. Now, let us look at the last procedure, that is deletion or removal from a AVL tree. Again, removal would mean removal as though in a binary search tree, which again takes order log n time, and restructuring the tree in the worst case might happen to be checked right up to the root of the tree, which might again take order log n time, right. So, if I am looking at a removal, your initial find is log n time, and restructuring might be required for all the nodes right up to the root of the tree, and we know there are precisely log n roots, log n nodes on such a path at most, the at most log n nodes on such a path. So, restructuring might be required at the most log n times. Each restructuring is going to require a constant time. So, when we say order log n, it actually includes a lot of constant factors. So, this is going to be order log n, which is initial find. Restructuring might be done log n times. Each restructure would take a constant time, right. So, each restructure takes a constant time. So, restructuring the entire tree in the worst case will require log n time. So, your removal actually is log n plus log n, which is again of order log n. So, removal also or deletion also in AVL tree would be of order log n, though the constant is going to be at least 2. So, we have seen that the disadvantages of binary search tree are overcome by using the height balance property as in AVL tree. All our operations now happen in worst case in logarithmic time. So, that is a substantial improvement over binary search tree or linear search, correct. Linear search and binary search tree in worst case were order n algorithms, whereas AVL tree all your operations happen in order of log n. So, that is a substantial improvement from linear to logarithmic. So, AVL tree is just one way of trying to solve the problem in a binary search tree. There are other approaches other than AVL trees. One approach other than AVL tree is doing what are called multi-way search trees. So, in a multi-way search tree is going to be a generalization of binary search tree like AVL tree is. So, it is AVL tree we know is binary search tree with some more property. Similarly, multi-way search trees are going to be something more than a binary search tree, which tries to overcome the disadvantages of binary search tree. It tries to do that in two ways. One is it allows you to store more information at a particular node. Until now, we were looking at trees, whether binary trees or binary search trees, such that we had only one single information stored at a node. We drop this restriction now, we allow more keys to be stored at one particular memory location. And similar to AVL tree, we also try to bound the height or maintain height of such a tree. So, multi-way search tree is one more solution to solving the problems faced by binary search tree. So, each internal node of a multi-way search tree is going to have at least 2 children. In this case, we will say that our internal node is a D node, where D is bigger than or equal to 2. So, D represents the number of children an internal node is going to have. So, when we say an internal node is a D node would mean it has D children. Now, rather than storing a single key, it stores a collection of keys, which is going to be of the form k x, where k is the key and x is an element. Now, each D nodes which is going to have D children, say labeled V 1 to V D, will store D minus 1 items stored in increasing order. Right. Recollect, a node is an internal node is a D node if it has D children. Now, D children we are simply labeling them as V 1 to V D, and this D node then is going to store D minus 1 keys, and these keys are going to be stored in increasing order at that particular node. So, this property allows us to store more information at a particular node. Finally, we try to generalize the property of the binary search tree. So, for each item k x stored at a node in the subtree of V rooted at V I, we have k I minus 1 is less than k is less than k I. So, this tries to generalize the binary search tree property. We will look at an illustration of the definition, and probably all these 4 points are going to be more clear once we look at an illustration. I am going to look at an example of a multi-way search tree. So, we start with 22. Now, it is a one node. So, if I look at it is basically storing one key. So, we have seen that if a node is going to store one key, then it is a 2 node, correct. So, this is a 2 node, and now the property 4 says that anything which is to the left of this has to be smaller than 22. So, this minus infinity and plus infinity allows us to store any key as small as possible than the keys which are present in the parent of that particular child. So, this is going to be less than this and this is going to be 25. Now, this is storing 2 keys. So, this is basically a 3 node, right. A D node is something which is going to have D children, and a D node is going to store D minus 1 keys, and they are going to be in increasing order. So, this is storing 2 keys 5 and 10 in increasing order, and it is a 3 node. So, it will have 3 children. So, 3 children which are going to be like this. So, the first is going to be less than 5, which is 3 4. The one in the middle is going to satisfy the property that the keys present here are going to be between 5 and 10. This is the generalization of the binary search tree property, and this is a rightmost tree. So, this is going to be this is the rightmost node. So, the key stored there is going to be bigger than 10. So, you have this level. Similarly, the other levels. Remember, right now your node can store as many as keys. So, at this level, last level, if I look at 14, on the left is going to be less than 14, on the right is going to be bigger than 14. Again, external nodes are used as placeholders, but it also is going to satisfy the properties of the multi-way trees. That means, this is a node which is storing 2 keys. So, it is going to be a 3 node, and 3 node will have 3 child. So, what we have here are 3 null nodes, correct. So, that is the key. So, when we say that we are looking at correct, this example. So, I am looking at, so if I call this as say V1, V2 and V3, I am looking at this as a 3 node, correct. So, if I look at keys which are here, correct. So, if I take a key here k, then it is going to be between k I minus 1 and k. So, this is going to be between 5 and 10. That precisely is the fourth property, which generalizes the binary search tree property. So, searching in a multi-way search tree is going to be similar to binary search. So, you start first with the root. We know if it is less than k1, it is going to be the leftmost child. We are going to check. If it is bigger than kd minus 1, we are going to search the rightmost child. If it is between ki minus 1 and ki, then we will check for vi. Right. So, let us look at this case. When we in this tree we are searching for key s equal to 8, we will compare it to 22. We know it is smaller than 22. So, we will go to the left subtree. Now, in the left subtree we have a 3 node. So, we will check where 8 lies in this particular 3 node. So, 8 we know lies between 5 and 10. So, we will try to compare now. So, once we know that it is between 5 and 10, then correct. So, at this particular you will have this as V1, this as V2 and this as V3, and we know as we compare 8, we know 5 is less than 8 is less than 10, we are going to search for 8 in V2, correct. So, at this stage we will shift our search to V2. Now, let us look at the other case where the search is not found. So, suppose we are searching for 12, again 12 is less than 22. So, we will search here, correct. Again this is a 3 node. Now, we know 12 is bigger than 10. So, we will search in the rightmost child of this node, correct. So, let me call this as say node V. We will search in the rightmost child of node V, which is V3, correct. So, we will going to search in V3. So, the search has come here. We compare 12 with 14. With 12 with 14, we know 12 is less than 14. So, we go to the left subtree and we come here. Compare it with the keys present in the next node, that is a 3 node. So, we will compare it with 11 and 13. What do I know is 11 is less than 12 is less than 13. So, this has now 3 children, it is a 3 node. So, we will compare it. So, we know this 12 is between 11 and 13. So, we will compare 12 with the keys that are stored in V2, but V2 is a null node. Therefore, this search is going to return a null node or is going to return an unsuccessful search. So, multi-way searching is just a generalization of a binary search tree, in which case instead of storing a single key at a particular node, we are allowed to store multiple keys with properties like binary search tree maintained in the tree. So, these are called multi-way search trees. If you look at the performance of multi-way search trees, we know for searching we have to is going to be proportional to height of the tree. Moreover, at a particular node we have to find, we can have multiple keys and we need to find search for the given key in the multiple keys, right. So, for example, if we were searching for 19, correct. If you are searching for 19, we would have finally reached here searching for 19, and we would have to find 19 in this particular sequence. We know at a particular node all your keys are going to be in increasing order. So, rather than trying to find sequentially there, we can use binary search to make our search efficient. Therefore, We know binary search is going to take us log time. So, this is what we get log D here, where D is the maximum number of children of any node, or in other way it is the maximum number of keys that you can have in a given node. Simple to observe that if D is constant, then your running time is proportional to height of the tree. So, like in AVL tree, we would like to keep height of this tree as small as possible. So, we move to what are called 2-4 trees or 2-3-4 trees. So, a 2-4 tree is a multi-way search tree. That means, it has all the properties that we had seen of a multi-way search tree, with additional 2 properties, in that a node may contain only 1, 2 or 3 items, and node with k items has k plus 1 children. That means, your node can be at most a 3 node. Right? So, 3 node means its child can store at the most 4 keys, and along with that it has what is called a depth property. That is, all the external nodes have the same depth. Correct. So, a 2-4 tree is a multi-way tree with a size property which is determined by fixing up D, and additional depth property which says that all the external nodes are going to have the same depth. So, this is an example of a 2-4 tree. So, at the root it is storing 2 keys 10 and 45. So, it can have, so it will have 3 children. So, we know that it has to again satisfy all the properties of multi-way search tree. So, the left will have keys less than 10, the second child or the middle child will have all the keys between 10 and 45, and the last child or the third child or the rightmost child will have all keys bigger than 45. This will also have all the external nodes as placeholders. So, for example, this will have, since it is a node which is having 2 keys, it will be a 3 node. So, it will have 3 external nodes or 3 null nodes at its children. This will similarly have 3, and this will have, since it is a node which is storing 3 keys, it will have 4 children, all null nodes. So, we see that all external nodes are at the same level. So, such a tree will be called a 2-4 tree or a 2-3-4 tree. We will stick to convention of a 2-4 tree. The key result that we are going to prove is height of a 2-4 tree. So, for proving that we need a small result which can be proved easily by induction. It says that a multi-way search tree storing n items has n plus 1 external nodes. It is easy to observe. Suppose you had all your n keys in a single node, then correct. So, for example, if you have this which is going to hold say k items, then what we know is this will have k plus 1 external nodes. So, the simplest case of your algorithm or the base case of your induction is when your height is going to be 1 and all your keys are stored at a single node. Then we see that this is going to have k plus 1 or n plus 1 external nodes. The proof is not difficult, can be easily extended to general n by induction. We will try to use this result in proving the main result that says that height of a 2-4 tree storing n items is of order log n. The proof is simple. Let h be the height of a 2-4 tree which stores n items. Then we try to find the maximum number of external nodes and the minimum number of external nodes that such a tree should have. And we know that that is going to bound n plus 1 from up and below. Now, let us look at upper bound on the number of external nodes that a tree can have. Now, at the first level, number of external nodes that you can have is going to be 4. So, I can have when at the first level you can have only 4 external nodes. So, that is the base case, that is when height is 1, you have 4 external nodes. Now, that is the what we are doing is the maximum number. So, maximum number, so your maximum number is going to happen, correct. For example, for your maximum case, you will have a something like this, say 3, 6, 9, whatever. So, and then you will have 1, 2, 3, 4, correct. So, height is 1 and there are 4 external nodes. Now, this can be, now if your height is 2, the maximum number you can have is 4 to power 16, that will happen, correct. For example, if all your nodes are going to be 4 nodes, right. So, if I take height 2, so you will have this as, correct. So, this is a 3 node, sorry, this is going to be a 4 node. So, this will store 3 keys. All this are also at this level are also 4 nodes, correct. So, we will have at this case, so height is 2 and so you will have at this level 16 or 4 squared external nodes, correct. So, if height is 2, then maximum number of external nodes that you can have is 4 squared. So, this can be easily extended by induction to a general case where we can say that if height is h, then the maximum number of external node is going to be 4 to power h, correct. We have already observed this for h equal to 1 and h equal to 2, can be easily extended for a generic h. Similarly, we try to find a minimum number of external nodes. So, we know each has to have precisely be at least a 2 node, right. So, we know each should have at least a 2 node. So, if I have a height with a tree with height 2 and which is a 2 tree, then it will have 2 squared external nodes, correct. So, these are precisely 2 squared external nodes. If you had height 1, it can be only this, and these are 2 to the power 1, correct. So, what we are observing is that if h is 1, it should have at least 2 power 1, if h is 2, it should have at least 2 to power 2 external nodes and can be easily generalized to arbitrary h. So, combining all these results, what we get is this expression. We know n plus 1 is the, if it has to store n keys, then it should have n plus 1 external nodes. If height is h, we get the connection between h and n, then n plus 1 should be at least 2 power h and is going to be at most 4 to power h. Then just taking logarithmic to base 2, we get that h is bounded above by log n plus 1 and bounded also below by log n, or your height is of order log n, which essentially proves the result that height of a 2-4 tree which is storing n keys is going to be of order log n. Thanks.